So welcome everyone. We are on the third day of this program called FACETS 2020, organized by IMSc. Today we have with us Professor Anirban Mukhopadhyay. He works on number theory, and he will be talking about primes via probability. Yeah, over to you, sir.
Yeah, thank you. Thank you for the introduction, and yeah, also thanks to the organizers for asking me to speak in this. So, as the title says, I will be talking about probability and also primes. So, primes and probability don't really connect to each other in a natural way. So let's start with probability. So very basic probability. So like every uh, so the I just simply start with the very elementary event of tossing a fair coin. So the possible events are getting an head, which I denote by H, and tail T, and the probability is half and half. So that would mean if you toss it 10 times, you are likely to get something like 5 and 5. But it need not be the case. So you might get like 4 and 6, or even less. Even you might end up getting 10 hits. But if you keep doing it more and more times, almost half of the time, or close to half the times, you are going to get head, and close to half the time you are going to get tail. So that's what happens if you are tossing a fair coin. So the coin is not biased towards head or tail. We consider a function, so call it x, from this set head and tail to 0, 1. So this is a function which takes value 0 and 1. And if we toss a coin, if we get head, we say that x is 1, and if we get tail, we say that x is 0. So we attach a numerical value to head and tail, and these are called random variables. You have already seen some probability in the first lecture, and you might have had courses in probability. So these are really very basic. So these are just random variables. So we are assigning some numbers, some real numbers, in this case just 0 and 1, to some events, some random events. And the interpretation of this first thing, that probability of head and probability of tail are half, in terms of this function, it says that the probability of x taking the value 1 is half, and x taking the value 0 is also half. So that would be the notation. So x and then some value. So this is the probability of the random variable taking some value. So that would be that this also defines the notation. So notation would be like this. So capital P are going to denote the probability, and usually capital X is random variable. Of course, I would always mention when it is a random variable. What are the random variables? So the next thing we are going to consider is tossing many coins. Suppose we have a bunch of coins and we are tossing them. So suppose we have 10 coins. Just be simple minded. So suppose we have 10 coins. We give them some name as C1, C2, C10, and so then we have 10 random variables. So what are these random variables? So the first one, x1, I call them x1 to x10, just name them x1 to x10. So the first one, x1, is again just exactly similar to the one we are considering when the x we considered above, when we considered toss of one coin. So it takes value 1 or 0 depending on whether we get head or tail. So if I toss the first coin, if I get head, then I say that x1 takes the value 1, and if I get tail, then x1 takes the value 0. So x1 is and so for the ith coin. So so I running from 1 to 10. So we take the ith coin, toss it. If we get head, then xi is 1, and if it is tail, then xi is 0. And all these events are independent. So just think about it very intuitively, that tossing of one coin doesn't influence tossing of other coin, meaning it doesn't matter what you get in the first toss for the second toss. So whatever, whether you get head or tail in the first toss doesn't have any bearing on what you get in the second toss, and so on. So all of them are independent, so they do not influence others. So that's the situation when we call they are independent. Of course, there are technical definitions, but don't bother about this one. So this is, so they are independent, and and now let's take a new random variable. So we just add them up. So this x1 and x1 through x10, these are all functions taking value 0, 1. We add them up, and that's again a variable from the head tail set, and this counts the number of h we get. So if you toss 10 coin, then x counts how many heads we get, because if we get tail, then the value of the variable is 0. So this simply counts the number of head. So with this very elementary thing in mind, we move to primes. So let's just go to the next page. So let's talk about primes. So what we intend to do is to associate to every integer, we want to associate a probability for its being prime. As such, it's a very ridiculous assertion, because an integer is either a prime or not a prime. There is no question of a probability. It's not a random event. So an integer is a prime or is not a prime. So a priori, this sentence doesn't have any meaning. You cannot associate a probability with to an integer which determines its primeness. So you can't do it. So what we are, so okay, let's go ahead. So then we would so better to explain it slowly. So what we are going to do. So you have to keep in mind that this as such, this doesn't have it doesn't work. So you cannot just attach a probability to an integer. So let's see. So let's go on slowly. So first thing is to count primes. So count primes. So here we are going to take help of a very non-trivial result in number theory, though proved more than 100 years back, but it's still a very non-trivial result. For a real number, x greater than 1, x greater than 1, let pi x, so it's usually denoted by pi x. So pi x is the number of primes less than equal to x. So if so this is number of primes less than equal to x. So for example, if x is 10, then pi x is going to be so it is the primes less than 10 are 2, 3, 5 and 7. So it's going to be 4. So likewise, and so for example, pi 9 would also be 10. Sorry, pi 9 would also be 4, because there are no primes between 9 and 10. So there were no changes. So but it's going to be an increasing function, that's for sure. So it's a big problem to estimate that function correctly. And prime number theorem says that this pi x behaves like x over log x for large x. So it's for large x. So it precisely speaking, it says if you divide pi x, the number of primes up to x, by this function x over log x. So if you divide it by that, then it goes to 1, it approaches 1 as x goes to infinity. So that doesn't quite mean that it's very close. It's close. It's going close, but for large x. So uh, it doesn't mean that it's exactly x over log x. So it can vary quite a lot. It's only in the limit that it goes to 1. So that's the understanding about counting of prime numbers. So of course more precise results are known. We would be seeing a little later. So at the time being, just remember that the number of primes up to x is about x by log x, roughly x by log x. So so now if we think of this event of hitting upon a prime, so if we just think of it as a random event, so we are looking at integers between 1 and x, and we are just picking integers randomly, then what is the chance of hitting upon a prime? So that should be like this. So the probability of getting a prime, if we are randomly sampling integers between 1 to x, should be this. That should be the number of primes up to x by number of divided by the number of integers up to x. So getting a prime is the events we want. So those are our favorable events, and the integers, all the integers between 1 to x is all the events. So that's the event. That's the total event set. So so it should be then pi x. Yeah. So in our notation, this should be pi x by uh, pi x by x. So this is the integral part of x. So this notation would mean this x box would denote the largest integer less than equal to x. So if x is an integer, it is x, and if x is not an integer, it's the integer just prior to x. So for a box of 5.3 would be 5, and box of 6 would be 6. Box of 5 would be 5. So and box of 5.9 would also be 5. So yeah, so pi x by x. So this is essentially like x. It's not very far from x. So if we are looking at asymptotics, so or so we just want to say it roughly, then this is just x. So box x is just x. So x over log x is the cardinality of the set of primes up to x. So that's in the numerator, and all integers, so that's about x, so that is in the denominator. So if you divide, then you get 1 over log x. So 1 over log x is roughly the probability or the chance of hitting a prime. If we are randomly sampling integers between 1 to x, then possibility of getting prime is 1 over log x. So we want to make these things precise, of course. So let's just try to understand it a little more clearly. So we in many steps we would go to the exact thing. So let's do it. Let's go back to the pointers. Let's go back to the pointers. So we for every integer, let's take a coin. So we have a coin, we give it a name, we call it Cn. So for every n, for every integer, we associate a coin. So we take a coin, we just simply take a coin and then toss it. So what we are saying that this coin Cn gives us head, so it flips to head with a probability of 1 over log n. So and tail with a probability minus with the rest, so 1 minus 1 over log n. So the probabilities are not same. So if it is a fair coin, we have seen that the probability of getting head and tail are half and half. So here it is not the case. So our coins are biased. So just imagine this situation that you have these integers greater than equal to 3. So in fact we are interested in larger integers, so just start from 3. So so we have all these integers, and for every integer we have a coin, but that and we are tossing it, but the probability of getting head and tail are not half and half, they change with the coin we take. So all the coins are biased, and the bias also varies. So the nth coin is biased in this way that head comes with probability 1 over log n, and tail with probability 1 minus 1 over log n. That's the rest of it. So it's either head or tail. So it has to be 1 for both. So so it has to sum up to 1. So so you can immediately notice that the probability of getting head becomes very small as n grows. So for a large n, the probability of getting head is very little. So as n becomes bigger, log n also grows. So log n grows with n. So then the probability of getting an head is becoming smaller and smaller. In fact, that is what we should be expecting, because we are so heads are going to give us primes, and primes are very few, because we have just seen that we have x over log x primes up to x. So it's a thin set. So for example, what is a thick set? So if you take all the odd numbers, then the number of odd number up to x is roughly x by 2. So that's a thick set. So it just so you have a constant. So this proportion is a constant. So the proportion of odds to all the integer is a constant, namely half. So here that is not a constant. It's 1 over log x. So it's becoming thinner and thinner. So primes are, in fact, as we know that primes are going far apart. I mean, but occasionally they comes close. Though that's the thing we would talk about a little later. Yeah. So occasionally they do come close. So that's an important aspect. Okay. So that's the thing we are doing. So so in fact now you can think of this. Okay. Let's go to the model that we are going to talk about. So we are going to now talk about some. So this process, we are just formalizing this process. So just remember that for every integer we have a coin Cn, which has this bias that the probability of getting head is 1 over log n, and probability of getting tail is 1 minus 1 over log n. Now, so this head and tail, like we have done in the first slide, we associate a number, and that is 0 and 1. So now this variable changes. So we need a variable for every integer. So given an integer n, so given an n, we have a random variable xn. So we associate a random variable to every integer n in this way. So with these probabilities. So probability of xn taking value 1 is 1 over log n, and probability of xn taking value 0 is 1 minus 1 over log n. So it takes value 0 and 1, no other option. So it takes either 0 or 1. So these are the probabilities, and this is so these random variables can be a possible model for primes, and this was first proposed by a mathematician called Harald Cramer in 1936. So, and this has been very useful. So this has been very useful. It's a very simple-minded model. So absolutely elementary model, just came from what we just discussed. So that's the kind of thinking which goes behind this, and but it's very useful, as we would just see. So yeah. So now we should just to address the thing that I started with, that you really cannot associate a probability to an integer of probability of being prime or non or composite. So we are not doing that. So what we are doing, so we we have these coins now. So essentially we have these coins, or you can think of these random variables. Either you think of this random variable or the coin. So you have bunch of them. So for every one, for every integer, and we toss it. If we get head, then we call n is a prime. So it doesn't mean it we don't mean that it's actually a prime. So if you get head, then it's a prime for this model, and if you get tail, it's a composite. So what we are doing, we are modeling it in terms of this. So it's a now our primes and composites are sort of models of actual primes and composites. So so that's the way to think. And why this should be useful, because as I said that the primeness of an integer is not a random event. It's either it's a deterministic event. Either an integer, a given integer, is either prime or not. So but why is it useful? So if we look, since we are going to look at average behavior, uh, uh, so this model is useful in studying average behavior, not individual behavior. So I mean, you are not going to, so given an integer, you are not going to use the model to determine whether that given integer is prime or not. We are going to model things like number of primes up to x, or gaps between primes. So we would see as we go on, we would discuss that. So let's have a definition. So just an easy definition. So now we are going to have our prime number theorem, a random prime number theorem. So that's what we are just gearing up to. So I for every for a real number small x greater than 3, I define this. So so define this. So pi x, so I just put x to distinguish it from pi x, which is actually the number of primes up to x. So just to distinguish that this is concerning this is a different, it's a random variable. So it's a sum of random variable, hence it's again a random variable. So you are summing up x3 to xx. So because you have all these for integers, so you are summing up. So if your x is an integer n, then you are simply summing up to x. Sorry. So then you are simply summing up x1 through xn. So if it is an integer, so integer. So then you are just summing up that. And then we look at the expectation. So what is the expectation of this random variable? So expectation is a linear function, so it gets added. So you add all the expectations individual of this individual random variable. So and all these random variables, so take value 0 and 1. So and it takes value 1 with probability 1 over log n. So for 3 it's 1 over log 3, for 4 it's 1 over log 4, and so on up to 1 over log this x box. So that is roughly this integral. So this is just the sum of reciprocals of logarithm. This is roughly this integral 3 to x, integration 3 to x 1 over log t. So it's roughly the integral. It's not precisely the integral, but it's roughly, and it's not a very bad estimate. So it's close to that integral, and which is again roughly x by log x. So I must warn you that there are errors. So there are big errors. So there are error, of course. So this is going to have error, but error would be smaller than this. So I just simply mean that error is going to be smaller than this. There are errors. I mean, if you just integrate it by parts, you would see that you can easily figure out second, third term. So it's going to give you a series, and so there are lots of errors. So, but errors are smaller than the first term. So we are happy with that. So as long as we are looking at behavior when x goes to x is large. So what we see is that this expectation of pi xx is what we get from prime numbers. So this expectation, or in other words, that's not this expectation, just this random variable. So this random variable models pi x. So it has similar behavior. So we have random model for number of primes. So that's the kind of thing Cramer was doing in 1936. So in fact, he has been doing it for some years, and then this paper in 36, he does a lot of things. In fact. So we would talk about some of it, little bit of it at least. So we have to again go back to primes. So when I say we go back to prime, we are going back to actual primes, integer primes, not random primes. So we would be going back and forth. So now we are back to prime. So size of nth prime is what we want to understand now. So let's list all the primes. So list them as P1, P2, P3 and Pn. So Pn is the nth prime. So this is the nth entry in our list of prime numbers. So P1 is 2, P2 the second prime is 3, the third prime is 5, fourth prime is 7, next is 11, 13 and goes on. So now let's look at this pi of Pn. So we take the nth prime and look at pi of Pn. So pi of Pn, so what is it? So it counts number of primes up to Pn. So Pn is the nth prime. So if Pn is the nth prime, then number of primes up to Pn is precisely n. So it's exactly n. So pi of Pn is exactly equal to n because there are n primes up to that. So we know that we know that pi x is asymptotic to log x. So if you don't like the language asymptotic to, then just think that it is roughly equal. Just intuitive approach is fine enough. So that it's roughly x by log x. So if pi x is x by log x, then pi of Pn is Pn by log of Pn. And that's roughly, so it is, this is roughly this, so we can say that this is roughly n. This is precisely n, but this is roughly this, so we can say that it's roughly n. So this is pi n by Pn by log of Pn is roughly n. Now we take logarithm of both sides. So we just take logarithm of both sides. So we apply log of both sides. So take a log here, and this is log here. So that's log of n. So then what do we get? So we get log of Pn minus logarithm of log of Pn. So log of log. So I like to just write double log. So log Pn. Yeah, in fact, number theorists are very happy to always like this write this iterated logarithm. So their favorite functions are iterated logarithms. So taking logarithms, what we get is log Pn minus log Pn, and that is about log n. So if I take this log Pn, and then this is 1 minus double log of Pn by log Pn. Double log is very small. So double log is very small. It's much smaller than log Pn. Therefore, this part, this part essentially goes to 1. So this just goes to 1. So since double log of Pn is much smaller than log Pn, it simply goes to 1. So what happens is the following. So this log Pn is essentially log n. So because this is about 1, this is roughly 1. So log Pn is about log n. Now what we have seen here, so let's get rid of these logs. So what we have seen here is this, that log that Pn is this. So that would mean that Pn is roughly n log Pn, and we have seen that log Pn is roughly log n. So this is n log n, and that is what I have written here. So therefore, the nth prime Pn, just recall that Pn is nth prime, so that is n log n. So the size of nth prime is about n log n. So all these are roughly. It doesn't mean that if you just take an n, say something like 100, and then just say that it is exactly that, it's not correct. So there would always be some error. So it is it's about n log n. For large n, that's even more true. So it would be closer if you take a large n. Then so far, and yeah. So the next thing is to see gap between primes. So now we have some handle on the nth prime. We know how big it is. So let's look at this Pn. So Pn is about n log n, and so the n plus 1th prime is n plus 1 into log n plus 1. So which is roughly n plus 1 into log n, because log n plus 1 and log n is not much different. So they're just almost the same. And this is n log n plus log n, right? So n log n plus log n. So and nth prime is about n log n. So if we just subtract nth prime, so if we subtract nth prime from subtract nth prime from n plus 1th prime, so just the difference of the consecutive primes, it should be about log n. It should be about log n. So that's what we would expect. Should be about, not precisely log n. So that's, in fact, that's the question we want to ask. So yes. So yeah, let me explain what I am saying. So this is just recalling from the last page that the difference between the n plus 1th prime and nth prime is expected to be about log n. Now we can ask a question. So how often the difference is less than that. So suppose half of log n, or twice of log n, or even bigger than twice of log n. So how often it varies? So it's around log n, it can vary. So, and how much it varies? How often it varies? So can we answer these questions? So even more precisely, let's form a precise question. In fact, this question. So what we now ask is this. So let's take any real number, alpha and beta. Alpha is so it's 0 less than alpha less than beta. Both are positive reals, non-zero positive reals, and alpha is less than beta, strictly less than beta. Strictly less than beta. It can be very big. So and then count all the n up to capital N. So all integers up to capital N. Capital N need not be an integer, so just in capital. So then what we count is the n plus 1th prime minus nth prime, so gap between these two primes. So this is the gap we were discussing just in the previous page. So this gap by log n. So that is what we want to ask, that if we divide it by log n, then can it be smaller than half, larger than half? So so it's a general situation. So I'm, instead of half or 2, I'm just taking half and instead of taking half and 2, I'm taking alpha and beta. So we asked that how many such gaps. So you can think of it as a normalized gap. So we just divided it by the expected size, so which is log n. So how many such things are between alpha and beta for our choices of alpha and beta? And let's look at the density of such things. So if you what we are considering, but in otherwise I mean, just think of this as we are counting the set, and it's like a probability. So these are the things happening, and then we divide it by 1 over the number of integers. So that's capital N, whether it's an integer or not, it's roughly the number of integers. It's not an integer, so it's just a real. So 1 over capital N. We do that, we do that, and then take n to infinity. So we want to see a very average behavior. So this is what is called density, asymptotic density. Okay, so if you are not familiar, then it's fine. Just this limit. Just think about this limit. Uh, so suppose the limit exists. So if when it's not even clear whether this limit exists, so can we say something about the limit, or can we say that it exists? So something about it. So far we were in the integer primes. We are actually talking about primes. Now we start to use the model. So let's use the model. So this is the first instance in this discussion that we are using the model. Let's start using it. So this is the question we are trying to address, that when is this gap Pn plus 1 minus Pn falls between alpha log n and beta log n. So this is what is the thing we are up to. So suppose that happens. So suppose this is what is happening, and let's call this gap. So let's say H is Pn plus 1 minus Pn. Let's say that. So let's call this to be H. That's an integer. So then this H is an integer, and it lies between, so this H is an integer and it lies between alpha log n and beta log n. And what is happening? So Pn is a prime. Pn is a prime, that is the nth prime, but n plus 1 is not a prime. So if I add 1, it's not a prime, then add 2, it's not a prime. So I can add up to H minus 1, and all of them are composite, then I get a prime. I mean, that is how it is. So that's the reason the gap is H. It has to be like that. So if you keep adding 1 to H plus H up to H minus 1, then you don't get prime, you get composite numbers. Then finally, when you add H, you get the next prime. So that's why the gap is H. So this is the gap. So now for fixed H, the probability of such a thing. So what is the probability? So probability, so of so all these Pn plus 1 to Pn plus H minus 1, all of them are composite. So their probability is 1 minus 1 over log of Pn plus J, and J is running from 1 to H minus 1. And finally you have a prime. So the probabilities are, just remember that the composite has probability 1 minus 1 over log n, and prime has probability 1 over log n. So that's the model. So now we are employing the model. So this is what it is. We want to have some idea of what this quantity is. So we have a we know how big Pn is in terms of n. So we use that. So let's just do that. So okay, now this is for a fixed stage. So this is for fixed stage. So now we vary H. So H is running from alpha log n to beta log n. So we sum it over. So the probability is summed over. So the total probability So of course we assume independence. So everything is, all these events are independent. So they don't influence each other. So we add them. So once we add them, and we also note that, so these are not so cumbersome because we know Pn is like n log n, and log Pn is like log n. That is what we need here. So Pn is like log n, and h is much smaller than n. So h is just between alpha log n and beta log n. So it's much smaller than n. So you can simply ignore this and think of it as log Pn. So if this is roughly log Pn, and that is like a log n, so I have 1 minus 1 over log n, and that the same thing is multiplied h minus 1 times. So the power, I raise it to the power h minus 1 into this probability. So this gives you this gives you this. So and then we sum over h, between h lying between alpha log n and beta log n. H is an integer. And now let's look at this thing. So this one, that's the cumbersome term now. So 1 over 1 by log n power h minus 1. So that okay, so that's just a notation that so it's a huge thing. So what I'm doing is so if I have a say so say I have an x and I'm trying to write it e to the log x. So I'm writing it in this way. So it's just not a fancy way of writing, it's actually useful. So this is what I'm doing. So this thing I'm writing it, so if this is x, then I'm writing it as exponential of logarithm of x. So that is what I do here. And this writing this large thing on top of exponential is difficult, so I use a notation which is exp of x. So exp of x stands for e to the x. So this is what it is. So if I take exponential of logarithm of this, so logarithm is so logarithm of this whole thing, so h minus 1 into log of this one. So which is log of 1 minus 1 over log. And so log of, so here what we use is this fact that log of 1 minus x is roughly minus x. So log of 1 minus x is roughly minus x. The other terms are smaller. So for a small x, so this holds for small x. So very small x, namely smaller than 1 of course, and maybe very small. So since we have n and n becomes bigger, so our x is very small. So our x is 1 over log n. So that's very small. So for small x, so small meaning I would really mean very small. So for small x, the log of 1 minus x is about minus 6. So other terms are much smaller. So like the next term is x square by 2. So those things are much smaller. So because x is very small. So that is now, so I replace this log of 1 minus 1 over log n by 1 over log n, minus 1 over log n. So I'm replacing this by log of 1 minus x by x minus x. So that is what it is. So minus 1 over log n. So minus 1 over log n, and as h minus 1 was there. And h minus 1 and h is not much of difference. So that is that can simply be replaced by h. So what we get is exponential h over log n. So of course this calculation is roughly done, but so what we are trying to do is to determine a behavior. So these things are for predictions. So, but it can be done quite precisely. So all these error terms can be found out, but so all the deviations, whatever, so it can be done very precisely. This calculation at least, but it's of no point, it's of no use. So it's just roughly understanding the size is good enough. So So what we have now is this. So that was the main part. So this whole thing is now roughly exponential. So e power minus h by log n. So we have shown that. So this part is this, and then I have 1 over log n. And of course the summation over h remains fine. So what we have, 1 over log n exponential of h by, so this as I just was saying, so this is e to the minus h over log n. So that's the notation for this. So yeah, so just to make it easier to write, I introduce this ext. So exponential of minus h by log n, and you have a 1 over log n, and then you are summing over h. So that is going to be roughly equal to the integral, just the corresponding integral. I replaced h by a continuous looking variable t, so you don't really take, you don't write usually h in integrals, so I take a variable t. So exponential of minus t by log n, integrated between alpha log n, which was the limit, alpha log n and beta log n. So just the corresponding sum, just the corresponding integral. And if I just make a change of variables, so we replace t by log n. So it's natural to replace t by log n, and we replace t by log n by u. Then what you get is an integral between alpha and beta e to the minus u du. So what do we now say? What do we now say? So what we started with is by looking at the probability of this event. Probability of, so we tried to calculate the probability of this thing happening. So we ended up getting this integral. So now we can make a conjecture. So with this calculation, we make a conjecture, and what is that? So we can write a precise conjecture. So we can write a conjecture. So this limit is now expected to be this integral. So integral of e to the minus u between integrated between alpha and beta. So that is what is expected. So if you are familiar with some probability, then you would see that this is like an exponential distribution. So we have calculated this limit. So we know the density of such things happening, the probability of such things happening. This is actually very difficult to prove. This is not known yet. This is not known. I mean, this is the proving this would be a big thing. And so just with using this elementary probability, we could make such a conjecture. But this has very interesting consequences. So let's just talk about one consequences. So just see that. So now if I take this, so here what we have is alpha less than beta, and this is all positive. So if I take beta to 0, so of course alpha would also go to 0. So if I just let everything go close to 0, then what we can say, that limit infimum of this quantity, this gap divided by this log n, is 0. And similarly, if I let this integral, this alpha goes to infinity, then we can say that lim sup is infinity. It just goes to infinity. So what does it mean? So it means that there are gaps between, there are infinitely many gaps between primes which are smaller than log n. I mean, smaller meaning as small as you wish. So because this limit infimum is going to 0, and limit supremum, so you can get larger and larger gaps. So that's the thing. So in fact, these results itself are difficult to prove. Now in fact better results are known, but this was proved in 2004 by so better results are known. I would just so Goldstone uh, Daniel Goldstone, Janusz Pinch, and Hildirim. Yeah. So one American, one Hungarian, and a Turkish mathematician. So they proved it in 2004. It was a landmark result at that time, but we now know better. So we now know better, and same for the Limsuk. So Limsuk was also proved some years before this, but we now have better results. Much better results are known. But nevertheless, these are not easy to prove. So this elementary probability sort of gives us a way to make conjectures which are valuable, very valid conjectures. So we can ask another question and another conjecture. So another question. So fix lambda, a real number, a positive real number, and an integer k, a positive integer, natural number k. So now question is, how often this interval n to n plus lambda of log n, this interval contains k primes. So we are now binding the number of primes. So we want to know what are the, how many intervals are there of this form which contains k primes. Then is this difference. So this is the number of primes up to n. So this exactly counts the number of primes between n and n plus lambda log n, and we want to say that when is it exactly k. So how often this happens? So we formulate a conjecture just like this. So we count all the integers up to n such that this difference is k, and then divided by n, and then limit. So that is, as you know, that this is the asymptotic density what we are talking about. So that gives this. And if you are familiar with these things, then some probability, then you can see that this is Poisson distribution. So this has Poisson distribution. So it's a very surprising thing. It's a very interesting and surprising thing, and you can easily come up with conjectures with this model. And this is also believed to be true, but far from being proved. So these are difficult questions. In fact. Then yes, so this is my so what I should do now in the remaining time, I think I would skip a little bit of this, uh, and so far what we have seen is that the model is great. So the model Cramer proposed is great, and it can make all kinds of conjectures, uh, but the thing is, it's not so nice all the time. So I would point out a few things. Don't have a lot of time left, so I would skip this prime number part. So let me just skip a little bit of this, otherwise we won't get to this. So okay, so I would just, in passing, I would just mention one conjecture by Cramer. So that is a conjecture which he predicted from the model. So depending on the predictions from the model, he made this conjecture in that same paper, 1936. So what was the conjecture? So for an integer, so this is what I am talking about. So this conjecture. So for a real number greater than 3, gx be uh, the largest possible gap between primes up to x. So this is what exactly that. So this gx is the largest gap. So given a x, you look at all the primes less than x and look at their gaps, and the largest gap is gx. So gx is just the largest gap. So Cramer predicted that largest gap should be log square of x. In other words, as x goes to infinity, this gx by log square x should go to 1. So that was the prediction, and it's called Cramer's conjecture. It's a celebrated conjecture, and this is also expected to be true, but this 1 is questionable. So 1 is probably not true. So there is some other constant, not 1. So there is some sort of deeper mystery in this. So it's not 1. So that is, but it's expected to be essentially true. At least this log square x size should be true. So that is the Cramer's conjecture. Now, so what we should just take away point from here is that the largest expected gap between primes up to x is about log square of x. So that's the takeaway from this point. And I go to a result which supports that. So let me, I would just skip this. So I'm talking about flaws of the model. So there are many flaws, but I would skip this one. This will take time. So I'll just skip that. So yes, so I'm talking about irregularities. So the situations where the model fails. A question is of interest is this. So if I take, and so what does this quantity mean? So this quantity is just the number of primes in this interval x2 x plus y. So between x and x plus y. So these are primes between x and x plus y. So when is so the question is, so yeah, so let's try to make sense what I am asking. So this is, so let's go back to prime number theorem. Okay, I should have kept a little more space here. So what I'm trying to say is this, that pi of x plus y. So suppose we are looking at a y which is small compared to x which is small. So suppose square root of x, something much smaller than y. So we would be even talking about even smaller things, but then let's see that. So pi x of this is roughly x plus y by log x plus y. And since y is much smaller than x, so we would expect this to be log x plus y by log x. So this is going to be roughly dominated by log x. So log x plus y would be roughly log x. So y is, say, smaller than square root of x, and pi x is x by log x. So if I subtract these two, that's what we are doing here, then we would expect this to be y by log x, to be roughly y by log x. So that is what we should expect. So when does this hold? So that question is, when does it hold? Now the Cramer conjecture says that the largest gap between prime is log square x. So if y is very small, if y is smaller than log square x, then these things may not happen. So we should take at least y reasonably larger than log square x. So we expect this to hold, that this number of primes between x and x plus y to be y by log x if y is somewhat larger than log square x. Suppose 10 times of log square x, or maybe little larger, some maybe some bit more power of log n. But we are interested in smaller ones, not large x, not large y. Large y is easier to deal with. So we want to look for primes in small intervals. So a result supporting this was proved by Atlas-Selberg in 1943. So and this is proved under Riemann hypothesis. If you do not know what is Riemann hypothesis, it's perfectly fine. It's an unproven conjecture which lies very deep. So anyway, so what he proved that this holds, but not for every x, almost all x. So there are exceptions. So the set of exceptions. So in technical terms, it forms a set of measures 0. But you can just think of that set of exceptions doesn't contain an interval. So it's like a sparse set. So maybe a countable set. You can just think of the countably many exceptions. That would be a way to think about it. very few exceptions. Infinitely many, can be infinitely many exceptions, but sort of far apart. And so almost all x. And that happens if y is somewhat bigger than log square x. And not only just a constant multiple of log square x, but the quotient should go to infinity. So if I replace y by say log 100 x, then it's fine, or even log 10x is fine. So some log power should be fine. So that is what Selberg proved, and this is expected to be true for all x. And unconditionally, this is a conditional result, it's under Riemann hypothesis, but it's expected to be true. That was the thinking at that time. So in fact, Selberg's result strongly supported it. Then the one of the biggest shock came in 1985 with the result of Helmut Meyer. So I would just say that. So that's probably the last thing. So so a very surprising result. So let me try to explain that. So what he proved is that for any b, so you can think about b to be say 100. We were just thinking about 100. So let's say b is just 100. So given this, there exists a delta b, some delta, some constant, some positive constant, non-zero positive constant, and arbitrarily large values x plus and x minus, and just these are notations. So arbitrarily large real numbers, such that this quantity, so this is again the number of primes between x plus and x, so between this x plus and this log of this. So in this, so this is an interval of length log bx x plus. So x plus is just notation. So and this is bigger than 1 plus delta. So whatever delta we got here, and this. So if this is y, so if I say that this is y, then this is y by log x, right? This is y by log x, and this is a constant. So this is this constant multiple of y by log x. But that's very unexpected. That's very unexpected because we expected it to be just 1. So this constant to be just 1. So that is what it is. So we just expect this to be 1. So this gap should be just 1. But here we have something huge. So some positive thing. So it essentially says that the prime number theorem fails in this kind of small intervals. So in this kind of intervals, log powers. So so whatever Selberg proved here for almost all x cannot be extended to x. There are exceptions, and very strong exceptions. So this is what was a shock at that time and changed the view. So the probabilistic modeling predicts a lot of things, but there are flaws, and there are more flaws than this. So this is not the only flaw, but some flaws can be mended. So you can repair some of them. So you can just add something to the model to bypass those flaws, but this is just not possible for this situation. So it just shows a complete failure for intervals of this kind of size. So if you have a interval which is of size of power of log, then the model fails. So it cannot be reconciled in this situation. So the model has done very good things. It's still doing. It's giving a lot of conjectures, and it shows what to ask for. It just gives us. It's a very good, very nice tool to heuristically argue, and to understand what to expect So I mean, once you know what to expect, you have a slightly better grip of the problem. So that is what is the success of the model. So yeah, my time is up. Actually, I'm past 5 minutes, so I'll stop there and for questions.
Yeah. Thank you, sir, for such a nice talk. Uh, yeah, so we can have some questions from the audience. Uh, Anyone can unmute and ask.
Hello, sir. I have a doubt.
Yeah.
Sir, when we were considering the size of nth prime, we considered pi of pn to be the number of primes less than or equal to pn, but then we clearly noted down that it is equal to n. So I actually didn't get how that will be equal to n.
Okay. Okay. I'll just go back to that page. Yes, I understand. I'll just go back to that page. So let me just switch back. Uh, yeah, it's one of the first thing. Yes. So yes, here. Yeah. So Pn is the nth prime. So nth prime. So if you look at this nth prime, then why is it nth prime? Because up to this you have. So for example, let's take small numbers. So if you look at the P3, if you look at P3, then you have 3 primes up to this. So you have 3 primes. Similarly, if you look up to nth prime, if you just go up to nth prime, so you would get n primes. So if I am looking at integers up to Pn, then I would be getting n primes, exactly n primes. So that's the reason it's nth. And in the notation, I should say that this is included. So yeah, if that is a conclusion. So pi x is the number of primes less than equal to x. So x is included. It's up to that. So if I am going up to Pn, then I would be getting n primes. So that is what it is. So is it clear?
Yes, sir. Yes, sir.
Okay.
Sir, on the same page,
Yes.
sir, I am Chandan. On the same page, on the bottom, you proved that log Pn is almost equal to log n.
Yes, right.
So why we are here? My doubt is that why we are not taking anti-log here. Is it because log is a flattening function, so Pn and n could be very different, but log Pn and log n might be very near. Is it due to that?
Yes. That is what so these are all for, as I was saying, that these are all for large n. So for large n, the double logarithm function is very small, and this kind of quotients just go to 1. That's the reason they are. Yeah. So in fact, Pn is certainly not like n. In fact, that's what we are proving. In fact, so Pn is like n log n. So Pn is like n log n, but if you take then log Pn, then this is log n and double log of it.
Okay.
And double log is very small, so to say, so much smaller compared to log n. If you want to say more precisely, then this is log of n. So double log of n by log n is going to go to 0 as n goes to infinity.
Okay.
So that's the reason. So yeah, so Pn and n are not really close, but then this is they are logarithms are close.
So, sir, we can take from this that we should be careful about before taking anti-logs.
Yeah, certainly.
For large n.
Certainly. Yes. So no, here we are not taking anti-log. Here I am
Yeah.
not taking anti-log. No. Here I am not taking anti-log. I am simply using this.
Yeah, that I understood, sir. That I understood.
Yes. So
My
simply
question was why we are not taking anti-log. Yeah, I understood that part, sir.
uh, yeah. So anti-log is not going to work because that's not even true. Yeah.
Yeah.
So you can't do that. Yeah.
And one more question, sir.
Yes. I mean it's not an equality. So.
Yeah, one more question,
Yeah.
sir. Sir, you said like x upon log x is the probability of no number of primes less than equal to n is x upon log x,
Right.
and from that probability comes 1 upon log x,
Right.
and then when you equate it to number of heads, then how it is exactly coming to be 1? Number of heads equal to 1 upon log x. In this here only, sir, here only.
Right. Yeah. So the probability is about log x, and so this what we are doing here is the rough idea. What we should do, and this is more precise. So we are just associating these points and then writing down their probabilities. So we have, as you notice, that we have changed it to log n.
Yeah.
So we have changed it to log n. So because of that, so here in fact, So here in fact we are essentially saying that everything has same probability, 1 over log x.
Yeah.
Wherever the integer is, it's the same probability. So this is very roughly done. So this is just to get an idea of this function. So we just this rough calculation gives us an idea that what to expect. So we should be modeling on that.
But this
So
this is the
prime number
probability,
I'm sorry.
sir. This is the probability of getting prime numbers less than x.
Yes.
Yes.
Yeah. So, but no, as I said that you can't really associate probabilities. So we are just here in this we are just starting to model. So
Okay.
for every integer we take a coin. What we mean is that we don't now consider the primes and non-primes. We don't decide that. We just take a coin, and if we get head, then this is the so and we just assume that the probability of getting head is 1 over log n, and probability of getting 10 is 1 over log n.
Yeah.
So
Yeah.
that's how we do it. We don't. So we are sort of going away from integers and to this probabilistic model.
Yeah.
So that's the point we start the model.
Yeah.
And then in the next thing we make it even more precise,
Yeah.
just saying that random variable. So we now moved away from the from actual primes.
Yeah. Thank you, sir.
Yeah, so we have a question in the chat. So can you see that?
Yeah, sure. Chat. Slide 3. Slide 3. How the integral was approximated. Yeah, so the integral is approximated just by using Riemann sum. So if you use Riemann sum, it's going to be close to that. Yeah, it's not. I mean, so what I mean is that there would be error, but that's the first term. So so that's the expected. That's the way. Just considering Riemann sum.
Yeah. Also, there is a question in the YouTube chat. Harshul is asking, what is the order with respect to n or log n of the error in our results?
Okay. Yes. Good question. So yes. So there were lots of error. So to start with, the prime number theorem. So prime number theorem has a huge error. In fact, so the error is of the size. So just this O notation, don't bother about this, we are just hiding a constant. So this is x over log x square. So that's massive, actually this is a very big error. It's smaller than this, smaller than the first term, but it's a large error. So in fact, that's the reason we don't write prime number theorem in this form. So the better form is this, that pi x is an integral 2x dt by log t. In fact, we saw a glimpse of that when we were considering the random model. So this is logarithm of t. So this integral, and then the error. So the error is then about so then the error is about say error is bounded by so in absolute value. So x you can take it to be this. So exponential of so yeah, maybe it's not a yeah, it's a bit cumbersome. So I would just say what is expected. So it's expected that the error is half plus, so square root of x, about square root of x, square root of x plus little more. So little more, and that little more will give you a constant. So for any epsilon you get a constant c epsilon such that error is bounded by this. But this is not yet known. What is known is much worse, much larger error, but this is what is expected. And this is equivalent to the celebrated Riemann hypothesis. This size of the error is equivalent to Riemann hypothesis. So of course then you can understand that it's going to be very difficult to achieve this, even going anywhere close to that. So the known error is the known bound on error is much larger than this. Yes. In fact, sorry, I can add one more thing. I was actually thinking of talking about that. I can just show one more result, since this question of error is very interesting. So I would just few seconds. So I in fact had slides on that. So just let me go to so that is another set of irregularities actually. So so now that I have said that this pi x is actually like this integral. So then of course you can ask whether it's bigger than the integral or smaller than the integral. In fact, it was shown that infinitely often it's bigger and infinitely often it is smaller. So infinitely often it is bigger by such a quantity, so it's quite a big quantity, square root of x. So infinitely often it's big, it's much bigger than Li of this side. Li of this x is this integral. So it's the prime counting function pi x is much larger than the estimated value, and much smaller than the estimated value. So both happens infinitely often. That was proved in 1914 by Littlewood. Yeah, so that's an irregularity. So there were lots of irregularities actually. Primes are very mysterious objects. Okay.
So there is another question in the chat.
Yeah, sure. Oh yeah, here. In Cramer's conjecture, how does the log x factor? Yes, so in fact, by using Cramer's model, you can model this gap between primes also. Just using Cramer's idea, one can model this gap between primes, and that would give this conjecture. That would precisely give this conjecture. But it's a technical one. Yeah, so not difficult. Certainly not difficult. But it's a bit of technicality to show that log square x is actually the expected gap. Yeah, it is possible. It's very much comes from this very elementary model. Yes. Oh, there is another question. Is it coincidence? Yeah, no. So it's not really coincidence. There is strong reason. Yes, probabilistic reason for this. Yes.
Yeah, so any other questions from the audience? So if not, for now we can switch off the recording and maybe we can have